Last time we finished that this solution for temperature in that 1D steady state heat conduction in a distribution. And from there we found out the heat flux on the left hand wall and heat flux on the right side wall. Now function of x here t is the dependent variable and x is temperature and the surface temperature on the right hand side, which is at x equal to L. So all these things they influence the temperature distribution, but we are only telling this x as the independent variable and t is the dependent variable. Apart from this independent variable, the factors which also influences the value, these factors like g dot, k, l, t1 and t2, they are called parameters. They are called parameters because in a given problem, the value of x varies smoothly between 0 to L. And you can always find out a value of x in between two consecutive or in between two neighborhood values of x. And the variation of x is a smooth variation, infinitely small steps it can vary. That is why it is called an independent variable. But if you see g dot value of g dot, k, l, t1 and t2, these values they definitely influence the value of t, but for a given problem, this value of g dot, k, l, t1 and t2 they remain fixed. In a given problem, these values g dot, k, l, t1 and t2 they do not change. So it is these values are distinct from the nature of x. Even in a given problem, the x value changes smoothly, but in a given problem, the value of g dot l, k and t1, t2 they do not vary at all. They will vary as soon as you change the problem. The same class of problem, another problem can have a different value of g, may have the same value of k, may have the same value of L, may have a different value of T1, like that. So the problems are different because these values are changing in another problem. But so far as a particular problem is concerned, only x changes, x varies, and along with that, t varies. And in that given problem, g dot k, l, t1, t2, they remain fixed. Now these things, g dot l, k, t1 and t2, they are called parameters, and x is known as independent variable and t is the dependent variable. There is one more thing that I'd like to emphasize, that here we can write it as t is a function of x, then we can put a semicolon, and then we can list the different parameters like g dot comma k comma l comma t1 and t2. So how do we express t? T is a function of x, then semicolon, then list of parameters. So if t varies with xy and then there are a list of parameters, then we like to write t is equal to function of x comma y, then semicolon, the list of parameters. So the semicolon will be placed in between the list of independent variables and the list of parameters. And each of these independent parameters, they will be separated by a comma. Each of the parameters, they will be separated by comma. But in between the independent variables and the parameters, there should be a semicolon to indicate the segregation of the independent variables from the list of parameters. Now, if we write the equation like this, then even if we want to express the temperature distribution in terms of a graph, it is not possible because we can plot a graph only as a y versus x kind of thing, or at the most we can plot a surface as z as a function of x and y. But that surface plot, from there we cannot read any value. Whereas if we plot a graph of t versus x, then as a y versus x kind of thing, then for any value of x we can find out the unknown y. But because it is not a case where t will only depend on x, so we cannot plot a graph of t versus x, then because the value of t also depends on g dot l k, all these parameters. Then what is the way out? Way out can be, we can draw many different graphs for different combination of values of g dot k, l, t1 and t2, and again it becomes very cumbersome. If we plot all these things on a single graph paper with t versus x for different combination of values of g dot k, l, x, l, t1 and t2, the whole space
But
becomes
sir,
hello.
sir, all the parameters should be positive. That's it.
No, it may be in a particular case it may be negative. For example, even x can be negative, though x is not a parameter. It depends on how you choose the origin.
So
It
x is the variable, but the L and the G dot will be positive on
I,
both the
I,
sides.
I have got your question. What I am telling is that first I said no, it may be negative also. Then I am giving you an example where x is not a parameter. X is an independent variable. It can vary from minus zero point 0.5 to plus zero point 0.5. Yeah. T1 can be
Okay, sir.
minus
Okay, sir.
T1 can be minus 7 degrees centigrade. T2 may be minus 40 degrees centigrade, like that.
Okay, sir. Okay, sir.
So these values may be positive or negative. That is not important. But what is important is that if we want to plot t as a function of x on a graph paper, then what will happen to these values of, how can you how can you plot one single graph, because the graph will change with change of values of not only x but also change of values of g dot k, l, all these parameters. So what we require to do in that case, we have to draw all possible values of combination of g dot k, l, all those things, and that is also not possible. It becomes a millions of graphs will be there, and ultimately you will not be able to see any distinct graph. So there is a way out. The way out is that is what I am going to do now, discuss, is to reduce the number of what you call parameters. And for that, what we do is that we do go through a process that you are aware of, known as non-dimensionalization. Sometimes it is also called as a normalization process. What we will do is that if I express by rearranging this equation, if I write t minus t1 divided by t2 minus t1. So I write a new recasted equation in place of 5. If I write t minus t1 divided by t2 minus t1, then it becomes equal to this g dot l square by 2k whole divided by t2 minus t1 plus x by l. That's all. So if I bring this t1 on the left hand side, t minus t1, and divide both sides by t2 minus t1, then it becomes t minus t1 divided by t2 minus t1, and this term becomes gl square by 2k divided by t2 minus t1. This term becomes simply x by l. Now, if we examine term by term of this newly constructed equation, what is the unit of t minus t1 by t2 minus t1? That becomes a unitless, dimensionless quantity. If I write t minus t1 divided by t2 minus t1, that let us call that as theta, then the theta becomes a dimensionless number. So, what is the unit of x by L? That is again a dimensionless number. We can call it as x bar. Here it is a dimension x bar square. Here it becomes x bar. Now, what happens now is that if we write this as theta is equal to g dot L square by 2k whole divided by T2 minus T1. What is the unit of this quantity? GL square by 2k. If it is correctly derived equation, then the unit of this must be equal to the unit of this, because this is dimensionless. So the unit of this quantity, combination of g dot L square by 2k or g dot L square by k, should be also having the same unit of temperature. That has to be. And we can check also, we have checked once, that if you see g dot has a unit of watt per meter cube into meter square, so it becomes watt per meter, and here it is watt per meter Kelvin. So if you divide watt per meter by watt per meter Kelvin, it assumes an unit of Kelvin. So this represents some kind of a temperature quantity. So we can replace this whole thing g dot L square by k as equal to, say, let's say we'll give a new symbol g, capital G dot. So this becomes, the equation becomes theta equal to capital G dot into x bar minus x bar square plus x bar. Now if we examine this thing, here theta is the dependent variable, x bar is the independent variable, and what is the parameter, number of parameters? That is only capital G bar. There is only one parameter. So what is happening through this process? We are trying to also reduce the number of parameters. By combining the parameters together, we are creating a new parameter, that is capital G dot. Now what happens is that if I plot theta as a function of x bar, in that we can draw one graph for one value of capital G dot. We can draw another graph on the same graph paper for a different value of capital G dot. So like that I can draw a series of graphs having different values of capital G dot. So I can, on the same graph paper, I can express the dimensionless temperature as a function of dimensionless distance from the left hand wall with capital G dot as a parameter. Now that is what people try to do. The advantage is numerous. So this becomes the equation. Theta is equal to, if you write theta equal to t minus t1 divided by t2 minus t1, and if you write x by L as equal to x bar, such that this represents some kind of a dimensionless temperature, this represents some kind of a dimensionless distance, then that equation 5 becomes theta equal to capital G dot into x bar minus x bar square plus x bar, where G dot is this thing, is a dimensionless, you can say it represents some kind of a dimensionless source term or heat generation term. And the advantage is that for for a chosen value of G dot, I can plot a graph of theta versus x bar. For another value of G dot, I can redraw on the same graph paper theta as a function of x bar, like that. So on the same graph paper, I can have a series of graphs, each representing theta as a function of x with one specific value of G dot. Now, the advantages are that we, first of all, we can reduce the number of parameters, such that we can draw a series of graphs representing different values of small g dot, different values of k, different values of L, different values of T1 and T2. Now, suppose in this way you construct a series of graphs on a graph paper with theta as a function of x, but each graph is representing one value of capital G dot. There is another graph that is representing another value of G dot, capital G dot, like that. Now, suppose I want to find out for a problem where T1 is equal to say 100, T2 equal to suppose 40, K is equal to suppose 300, G dot equal to 300, like that. L is equal to suppose 0.05 meter. So in this way, now I want to find out at a distance of x equal to, I have taken the thickness equal to, if I write down those things, suppose, but I take a problem like this, that say that that heat generation is equal to, suppose, 200 watt per meter cube. P1 is equal to, suppose, 100 degrees centigrade. So T2 is equal to, suppose, 40 degrees centigrade, and your L is equal to 0.5 centimeter, means 0.05 meter. The unit should be consistent also. And suppose K is equal to 300 watt per meter Kelvin. Anything else is left? Nothing else. Now with this, if I calculate the value, I can calculate the value of G dot. Once I calculate the G, I want to find out what is the T value. T is equal to how much at, say, x equal to, suppose, 0.01 meter. I want to find out the temperature at a distance of 0.01 meter using that graph paper. I could either use that formula where I can straight away put the values of these things, the small g dot, T1, T2, L, the thickness, and the conductivity, and I can find out for this x equal to 0.01 what is the temperature. But in industry, they prefer to use sometimes graphs, and you have a graph like that with theta as a function of x bar, with capital G dot as different parameter. There are different graphs, and what I'll do is that I'll calculate what is the value of G dot for our case. G dot will be equal to this thing, 200 into L square, means 0.05 square, by twice of K, means divided by 600, divided by T2 minus T1 equal to 60 Kelvin. With that, I can calculate the value of G dot, and once I find out the G dot, also I can find out what is the value of X bar. What will be X bar? X bar will be equal to 0.01 by 0.05, that is 0.2. 1 by 5, that is 0.2. So I know the value of X bar equal to 0.2. I know what is the value of capital G dot. First of all, I can use this equation. Also, I can, in that graph paper, I can move to X bar. What is the range of value of X bar? X bar will vary between 0 to 1, because on the left hand side, X bar equal to 0 by L, that is 0. On the right hand side, X bar equal to L by L, so it is 1. So X bar always varies between 0 to 1. Although X can vary from 0 to 0.05 thickness, it may be for another problem 0 to 0.03 meter for another problem. Different problems will have different thicknesses. So we cannot represent all the things in one single graph. But if I make it dimensionless, then always our X bar varies between 0 to 1. What about theta? Theta, what is the value of theta on the at x bar equal to 0? It will be equal to 0, because at x bar equal to 0, that means at x equal to 0, that is the left hand side, t is equal to t1. So on the left hand side, theta equal to 0, and on the right hand wall, x bar equal to 1, and there theta is equal to 1. So at x bar equal to 0, theta equal to 0, at x bar equal to 1, theta equal to 1. But in between, it can have different values of theta. Theta, as we have seen, theta does not vary between T1 to T2. It varies, it may go up and go down. It may be even like this. If it is a heat sink problem, then somewhere the temperature may decrease. So your theta, although it is equal to 0 on the left hand side at x bar equal to 0, and theta equal to 1 on the right hand side where x bar equal to 1, but in between you can have different values of theta. So, but we can read these things from that graph paper. I know what is the value of x bar in my equation, in my problem. X bar equal to 0.2. So I can move to 0.2. Then I can read the value of theta. Once I read the value of theta, I can calculate the value of t as equal to theta into t2 minus t1 plus t1. Just 1 minute, I'll come. Hello, can you get my point that in this way I can use one single graph paper to to calculate the value of temperature for any value of x. If I know the value of x, I can find out the value of x bar. Then on the graph paper, I can see what is the value of theta at that x bar. And once I know the value of theta from the graph paper, I can calculate the value of t as equal to theta into delta t. This you can call it as delta t, t2 minus t1. Theta into t2 minus t1 plus t1 is your temperature. And this is how fruitfully we can use the graph to calculate the values very quickly. And another thing is that you can reduce the number of your parameters. So that is why most of the time, many a time, people prefer to use a dimensionless form of the equation that they develop rather than a dimensional form of the equation. And this process of reducing a dimensional equation into a dimensionless one is known as a normalization process. Now, we have started with a somewhat more complicated problem. We will now come down to a less complicated problem. The less complicated problem is this, that we have the same problem with no internal heat generation. We have a plain wall where there is no internal heat generation. And that is a more likely problem than a problem where the wall generates heat. Like our household walls, they do not generate any heat. Rather, they transmit heat from outside to inside during the summer, and they try to prevent loss of heat from inside to outside during the winter. Now, so if we want to know for an identical problem, except the fact that there is no internal heat generation, same problem, but this G dot equal to 0 and the wall is subjected to a differential of temperature T1 and T2 and thickness is known, conductivity of the wall is known, then how to find out the temperature distribution and how to find out the heat loss across the wall. Now, if you see in this case, if I make simply G dot equal to 0, then we get our solution. Just the temperature distribution that we have obtained already, that involves a more general case where there is a heat generation. And if we put G dot equal to 0, then you get the solution also for a problem where there is no heat generation. In that case, what will happen? T will become simply equal to T1 plus T2 minus T1 by L into X. So what we have is something like this. T equal to T1 plus T2 minus T1 by L into X. This is basically the temperature gradient in this, and the equation will be a linear one, and the graph will be a straight line. But in the case of a heat generation case, there it will be a non-linear equation because the equation is a quadratic one. X square is there. But so the moment there is no heat generation, x square term will go out, this term will go out. So it will become simply t will become dependent linearly with x. And even in this problem, you will have three parameters. T is the independent variable, x is the dependent variable, and the three parameters are T1, T2 and L. So by the same process, we can make it into dimensionless as theta, that is equal to T minus T1 divided by T2 minus T1 is equal to x by L. So theta becomes equal to x bar, and in that case the graph will be a straight line passing through origin, and that is the thing. Now here what it will look like, the heat flow will which way the heat flows, heat flows from the direction of the higher temperature towards the lower temperature. If we have taken a higher temperature as the T1 value and this value as the T2 value, then T2 minus T1 is a negative kind of thing. That's why what we see here is that as we increase the x, the value of theta increases. But in our problem, if we take T1 greater than T2, then T decreases actually with increase of x. So there is a decreasing temperature at increasing x. So what we can do, we can write it like this, that T minus T2 divided by T1 minus T2 as the equation, and then we can rewrite that equation in that way. We can see what happens. Now if we take this thing, that case, what is the heat flux in that case? When there is no heat generation, the heat flux on the left hand wall will be equal to simply K into T1 minus T2 by L, because this term is absent because there is no heat generation. Heat flux on the right hand side wall will be equal to K into T1 minus T2 by L. So what it indicates is that because it is a steady state problem, because it is a one directional heat conduction problem, then whatever heat flux enters through the left hand side wall, the same heat flux has to leave through the right hand side of the wall, because the two areas are the same. What is the heat transfer rate? That will be equal to K into A into T1 minus T2 by L, and here also the heat transfer rate will be equal to K into A into T1 minus T2 by L. Why this A comes? Because A comes because this is the heat flux part. If you multiply heat flux, which is a constant over the entire surface area of the wall, if you multiply that heat flux with area, you get the heat transfer rate over the whole area. So your heat transfer rate Ka T1 minus T2 by L, here also Ka T1 minus T2 by L, and this has to be because it is a steady state problem. So there is no accumulation or depletion of energy of the body itself, and also there is no other way for the heat to leave, because what could have happened is that if we take this problem, if you see the schematic diagram of the problem, certain amount of heat is entering through the hot wall and the heat is going out through the right wall. Why at all the heat is coming in and going out? First of all, let me answer those things, that it is a steady state problem. Okay, and in a steady state problem, if you want to maintain a hot surface continuously, and if you want to maintain another cold surface, what will happen is that heat will flow from the hot towards the cold surface. So heat will travel from this left hand surface towards the right hand surface. So as heat travels, the tendency will be for the temperature to fall. Now if it is to be maintained at a steady state temperature, then the only way we can maintain this temperature at constant at T1 is whatever the rate of heat leaving from this wall towards this wall, we must go on supplying the same rate of heat from the outside to this wall, hot wall. So there must be a continuous supply of heat to the hot wall, and that rate of heat supply must be equal to the rate of heat that travels from T1 towards T2. And by the same logic, the heat that arrives over here, what is the heat leaving? That is equal to the heat that you are supplying. The heat that you are supplying under steady state, that heat is leaving from this surface arriving at this surface. In fact, it is passing through each of these surfaces by the undiminished magnitude. Whatever the heat is arriving at any surface in between, the same rate of heat has to leave from that surface. Otherwise, there will be an departure from equilibrium. So, whenever more heat arrives and less heat leaves, then it means that it is absorbing certain amount of heat. If more heat leaves than less amount of heat it is absorbing, then there will be a fall in energy. If more heat leaves than the heat it is receiving, then there will be a fall in energy that will be manifested by drop in temperature. If more heat is received, less heat is lost, then there will be accumulation of energy. So that will be again reflected in terms of rise of temperature. So whenever there is a steady state condition, that means that whatever it is receiving as heat energy, the same amount of energy must be leaving that body. Then only it will maintain its constancy of energy, and then only the temperature will remain constant. So whatever heat is supplied over here, that heat travels through each and every layer of this body and finally leaves this body to the other surface. And what is that magnitude? That will be equal to K into A into T1 minus T2 by L. That K into A into T1 minus T2 by L, that is the heat that is going inside the body through the left face, that is traveling through each and every layer of this body and ultimately coming out of the body to the surrounding through its right face, through its colder face. So the heat is received by the hot face from the surrounding, and the heat is rejected from the body through its colder surface. Now coming back to this point, that this the heat received could have been different from the heat that is leaving under two different situations. One, that if the body stores certain amount of energy, then what will happen? Then the heat leaving will be less than the heat it is receiving, because the balance only it is storing. If the heat leaving is less than the heat it is receiving continuously, that means there is a continuous storage of energy which is equal to the difference between the heat received and the heat leaving. On the other hand, if more heat leaves than it is receiving, then there will be a continuous fall of energy level of this body, and so that will be reflected in terms of drop in temperature of the body. So if there is an unsteady problem, there is a possibility that the heat received will be different from the heat rejected by the body. There is another reason for which these two may not be equal. There may be another reason for which the heat received may be different from the heat leaving. That is when you have another escape route for the heat to come out. Now here what we have taken is that heat can come only along the direction of x. Heat travels only along x. It does not travel along y, or it doesn't travel along z. That is the direction perpendicular to the plane of the screen. It is only traveling along x. So there is only way it is coming through, coming in and going out. There is only one path. Like there is only one lane, and through that lane as many number of cars are entering, so many numbers of cars are has to go out. If there is no parking of any car inside, then whatever is coming inside that lane, the same number of cars have to go out of that lane if there is no by lane. But suppose there is another path heat can travel through. Suppose the heat does not travel only along x, it also travels along y. Then then the heat which is coming out plus the heat which is coming out through y phase, this summation of these two may be equal to this. So there may be another case where the incoming heat through left x may be different from the outgoing heat through the right x, if there is the heat also leaves through either y at equal to 0, y equal to h, or z equal to 0, or z equal to suppose depth d. So if heat travels in multiple direction, then this thing may not be there. That is the heat coming inside through the left wall and heat going out through the right wall. They will be same If the heat flow is one dimensional and if there is no accumulation of energy, that is, if there is no unsteady heat conduction situation. If the heat conduction is steady state and if there is only one directional heat flow, then the heat coming in through the x equal to 0 has to be equal to heat going out through x equal to L. And then we get this to equal, and that is given by Q dot, capital Q dot, that is given by capital Q dot, what is that thing? That is given by capital Q dot, which is equal to area into heat flux, that is Q at x equal to 0, that is equal to K into A into T1 minus T2 by L, and same value of Q dot will be applicable for the right hand side of the wall. Capital Q dot will also will be this too, because there is no internal accumulation, because the body is under steady state. There is no internal accumulation of energy within the body or depletion of energy from the body. And also there is no other way for the heat to travel. It can flow only along x. So this will be equal given by K into A into T1 minus T2 by L. And you can rewrite this thing as equal to T1 minus T2 divided by L by K. We can write the whole thing. I don't know whether it is written over there or not. That Q dot, which we find out as K into A into T1 minus T2 by L, that we can rewrite it as in the form of T1 minus T2 by L by K. Now, the reason for writing it like this is that it is something very similar to your Ohm's law for flow of current through a conductor, where we write the potential drop is the delta V divided by R is the current flow. It is also something like a heat flow is like flow of current. So the rate of heat flow is equal to delta T. The reason for heat flow is temperature difference, is the potential difference for which the heat flows, divided by the divided by resistance. This, the nature of this resistance is conductive. We call it R suffix conductive, and that is given by L by Ka. So the larger the value of this thickness, the thicker the wall, the more will be the conductive resistance of the wall. On the other hand, the larger the area, the smaller will be the resistance, and the larger the conductivity, smaller will be the resistance. So the resistance will be more if you have a larger length, which we call it as thickness, and smaller conductivity and smaller area. If the cross sectional area is smaller, if the conductivity of the material is smaller, it will have a higher resistance. On the other hand, if the length is larger, it will have a higher resistance. So resistance will be proportional to L and inversely proportional to K and area. So this is what we, many times we can write Q dot equal to delta T by R, but remember this we can write under those two situations, that first of all there is no internal accumulation of energy. It is under steady state and it is one dimensional heat flow. If there is one dimensional heat flow under steady state, then we can express this Q dot as equal to delta T by R, given by this form of the resistance L by K. Now we can have a situation where you have a class after this. Hello,
Yes, sir.
you have a class after this at 11.
No, sir.
No,
No,
sir.
no
No, sir.
class.
No, sir.
So can I continue for 10 minutes more?
Yes, sir. Yes, sir.
Yes,
Yes, sir.
sir.
Yes, sir. Yes, sir.
No.
Now, the case that we have considered in our previous example is a plane wall where we know the temperature of this side of the wall, we know the temperature of this side of the wall as T1 and T2. And then we can find out what is the heat loss across this wall. Now, why this is necessary is, suppose we want to design our wall so as to preserve the heat content inside the room. Suppose the room is constructed at a place where the climatic condition is cold. Then if we want to live in that room, we must have a comfortable temperature that may be around 24, 25, 26 like that. But if the outside temperature is low, say maybe around say sub 10 degrees centigrade, around 10 degrees centigrade, then what will happen? Inside temperature is hotter and outside temperature is colder. So heat will be continuously lost from the room ultimately to the surrounding. And this will cause a drop in temperature of the room air. So long as the outside temperature is colder and inside temperature is hotter, there is a tendency for the heat to come out of the room and it will be going to the surrounding. Now, so the net result will be the inside temperature of the room will decrease. So people will start to feel uncomfortable. Now, how can we manage this situation? Is if we can supply a rate of heat which will be equal to the heat lost to the surrounding. We cannot stop that heat flow from the hot room to a colder surrounding. There will be a heat loss. Now, what we can do is that the rate at which the heat is lost from the room to the surrounding through its wall, if we can supply equal rate of heat inside the room by maybe something like a room heater, then we can maintain constancy of temperature inside the room. The rate at which heat is lost by the air inside the room to the surrounding, if we can compensate that energy by supplying from an external source, maybe through an electrical heater, maybe through a steam heater, if we can supply same rate of heat into the room, then we can maintain constant temperature inside the room. Same is true in the hot climatic condition. If we want to design a room where the climatic condition is hotter, suppose the outside temperature is something around, say, continuously around 35, 30, 40, something like that. Then, and we want to maintain a comfortable temperature inside the room by maintaining the temperature inside maybe something around, say, 22, 23, 24 like that. So again, a reverse thing will happen. Then outside heat will come from outside wall towards the inside wall because the outside wall is hotter and the inside wall is colder. Heat will now try to travel from outside to inside so that heat is continuously added into the room. The room temperature will tend to go up, making the temperature uncomfortably high. Then what we can do? We can do just the opposite. That is, we can take out heat from the room and throw it into the surrounding. And that is what we try to do maybe through a heat pump. Through a heat pump, what we do is that we try to pump out the heat from inside the room and throw that heat into the hotter surrounding. Okay. So be it a climatic condition where it is cold, there we require to use a heat pump to supply heat into the room. And if it is a if it is a hot climatic condition outside, then we require to suck out heat from the inside through a refrigerator or something and take out that heat and throw it into the surrounding. Now, both ways we have to spend energy. Even if we want to add heat into the room for a cold surrounding, or even if we want to extract heat from inside the room for a hot surrounding, we have to spend energy. To achieve both of these things, we require to spend energy. Now, naturally, it becomes a costly affair, and so naturally our tendency will be to create something where we require to spend less. So what we would like to have is, first of all, if we can design a wall where the heat transfer rate is somewhat less, then we require to transact less amount of energy into the room. If the heat loss into the room is less, then we require to extract less rate of energy from the room. If the heat loss is less from the room to outside, then we require to supply less rate of energy into the room. So our objective will be always to design a wall in such a way that heat loss across heat transfer across the wall is to a minimum. So you require to know what constitutes that what we call heat. What will minimize the heat loss? The what will minimize the heat loss is by increasing the thermal conductivity of the wall and the conductive resistance of the walls, not thermal conductivity, the conductive resistance of the wall. And what we have seen is that if we make the wall thicker, then it will have a larger resistance. If we use a material that has a low value of conductivity, it will increase the resistance. Then the heat transfer rate will be reduced. But there are disadvantages to this thing. If you want to increase the thickness of the wall, then the carpet area of the room becomes less. So I can make the thickness of the wall maybe twice than what is being done presently. Do you know what will be the thickness of outside wall of a room? Any idea?
1 feet.
Huh?
1 feet.
1 feet is it is there, but it is there mostly in old houses. Houses which are 100 years old, at least like that, they have something like 1.5 feet because there the wall had a purpose to bear the load of the roof and the floors above. So the walls were load bearing walls in those days, and to bear the load of the entire house, it had to be made so thick. Nowadays, what they do is that the walls are not used for bearing the load. The walls are simply a kind of a barrier for your privacy so that the others cannot see inside, others cannot go inside, like a thief cannot enter into that. So for many reasons, and also to minimize the heat flow, you require to have those walls. To minimize the sound inflow, you require to have that thing. So you have to minimize the inflow of sound, you have to minimize the inflow outflow of heat, and also privacy is there, security is there. All these reasons you may require to hang a picture. So you must have a wall where you can put some nail and then you can hang the picture. For all these reasons, you require to have wall. Now, the outside walls are normally made, say maybe 10 inch, okay, and the inside maybe 10 inch or 5 inch, and the inside wall, that is the wall in between rooms. You may have consecutive rooms, adjacent rooms, and there may be a wall in between. That wall may be made of 3 inch. And if you see, the length of a brick is normally around 10 inch by 5 inch by 3 inch. You can orient the brick accordingly. If you want to construct a 3 inch wall, then you use that dimension like that. Now, what I am saying is that if you make a very thick wall, then ultimately it will reduce your usable capacity of the room. So you would like to have a minimum thickness of the wall. Then what you can do is that you can use a low conductivity material for the wall. And that is what is done in countries where the temperature is very low, surrounding temperature. There you can use some kind of insulating material than the conventional brickwork. You can use some kind of wooden structure or some other material where the conductivity is much lower, so that you can reduce the heat conduction across the wall. The whole study is towards that. We have to know what should be the, if you want to install an AC, your AC capacity should be more if you have more heat ingression from hot surrounding. So you can, and that becomes a continuous running cost. It is continuously you have to pay for. Whereas you can use this thing to minimize the heat loss. You can use a insulating material for the wall, and for that, once you do it, it becomes permanent. Then your continuous running cost for running the AC becomes less. Or if you are using a room heater in a cold condition, then also the purpose will be served. So this heat loss calculation is the primary motive for this particular set of examples that I am discussing so far. And we must know what is the rate of heat loss across the wall. Now, what we have seen is that heat loss is given by T1 minus T2, temperature difference across the wall, divided by the conductive resistance given by thickness whole divided by K into surface area of the wall. The question is, how do you know the value of T1 and T2? How can you know the T1, T2 values? We may try to measure the temperature by some device. But if we put a temperature measuring device on this wall, what it will give is an average temperature of the surrounding and the inside of the wall. If you if you if you touch a measuring device over here, if you put some thermometer bulb over here, then it will pick up energy from the wall, it will pick up energy from the surrounding air. So the temperature that it will indicate is some kind of an average temperature of the surrounding air versus the wall temperature. So normally what people prefer is not to know the temperature on the wall. The temperature of the wall they do not try to measure. What they do is that they move far away from the wall, somewhat interior to the room. It may be exterior to the room, and this may be interior to the room. Okay. Now, what they do is that they move far away from the wall, and when you move far away, what you can see is that after some distance away from the wall, if you measure the temperature here or here or here or here, all the while you see the same temperature that you say call it as suppose call it as T infinity 1, the free steam temperature on side 1. And if you call this side as side 2, by similar means, if you take away your temperature measuring device, it may be a thermocouple or a thermometer, if you move far away, then you will see that temperature is same. And that distance at which the temperature is same, that is beyond your thermal boundary layer. So this is inside the thermal boundary layer, where there is a temperature drop, is inside the thermal boundary layer, where there is a temperature drop. But if you go outside the boundary layer, you see the temperature is constant here and here. On that region where the temperature is constant, it is called a free steam zone. And the region within which the temperature varies near to the boundary is called the boundary layer. And so what we do is that if you measure it here, then it is all the while measuring the temperature of the air that is surrounding it, and you can accurately capture the temperature of the free steam over here, free steam over here. We don't try to measure the temperature of the surface, temperature of the surface. Now, heat has to go from this here. What has been shown is that there is a hot condition and there is the cold condition. Now, heat goes from the hot fluid towards the cold fluid. It passes through the wall. It passes from the fluid, then across the wall, then passes through the fluid, and ultimately comes to this space. So heat comes from the hot space to the cold space, traveling through the fluid, then through the solid, and again traveling through the fluid. Ultimately, it comes inside the room. And here, what you know is T infinity 1 for the ambient temperature on side 1, the ambient temperature on side 2. We do not know what is this value, what is this value. These are unknowns. One more thing that you know is that the heat flows from the fluid to the wall by convection, and that convection, there is a coefficient called convection coefficient that is known as H1. So what you know for this side is the T infinity 1 is known, the free steam temperature on side 1 is known, and the convection coefficient is known. Similarly, we know the convection coefficient on the other side, side 2, and the free steam temperature on side 2. These two we know. Now, if we see how the heat flows, the heat that flows from the left hand side, that is a hot fluid, to the side wall. Momentarily, although we do not know what is the temperature of this wall, let us assume this is equal to TS1, the surface temperature on side 1. And let us assume this as equal to TS2. If we know this TS1 and TS2, we know that the variation will be a linear one. That is what we have seen just now. That for a known temperature T1 to T2, the in-between temperatures will vary linearly. Here also from TS1 to TS2, the temperature varies linearly. But what happens outside, exactly the nature I don't know, but I know that there must be a temperature drop. Then only the heat can flow from the hot wall towards from the hot fluid towards the wall. The wall temperature must be less than this fluid temperature, then only heat will flow from the fluid towards the wall. And similarly, here also, the temperature of this wall must be less than the surrounding temperature, then only the heat will come out ultimately. So there should be a gradual drop in temperature. The nature of drop may be different here. In the fluid side, the solid side, it will be a linear one. And again in the fluid, there must be a continuous drop. So there is a continuous drop of temperature. Outside, there is a one nature of drop. Inside the wall, there is a linear nature of drop. Again, outside, there is another nature of drop. Now, if we see that there is a temperature difference of T infinity 1 to Ts1, then what is the heat flow by convection? That heat flow by convection will be equal to H1 into area, this area of surface area through which the heat is entering. H1 into area is A, suppose, into T infinity 1 minus Ts1. Similarly, the heat loss here, and they will be same, it will be equal to H2 into area into Ts2 minus T infinity 1. And that will be equal to Ts1 minus Ts2 divided by L by K into A, where L is the thickness of this thing. So that is what we have written over here, that this Q dot is the heat coming from the hot fluid at a temperature T infinity 1, traveling towards the colder wall. Colder wall means the outside wall whose temperature is less than this, whose temperature is Ts1, that is not known. This Ts1 we don't know. What we know is this. So the heat flow rate will be equal to H1 into area into this thing minus this thing. The free steam temperature minus the surface temperature. And the same heat travels as equal to K into A into Ts1 minus Ts2 by L, where again Ts1, Ts2 are not known. And that ultimately has to be equal to the heat that is lost from the surface Ts2 to the fluid that is at T infinity 2. There it is given as H2 into area into Ts2 minus T infinity 1, infinity 2. Here it is by convection. We have written the Newton's law of convection is the by conduction in the wall, and again by convection from the from the surface Ts2 to that inside temperature, side to temperature T infinity 2. Now this has to, they will be same. Why they will be same? Why they will be same? They will be same because we have taken a case where the body, the whole thing is happening under steady state and the heat flows only along one direction. So whatever the heat comes from the side one fluid to the wall, the same amount of heat goes through the wall does not store anything, and same heat goes out of the wall and ultimately goes inside the side number 2, and there is no other path the heat is escaping. It is all along flowing through one direction from left to right, and there is no accumulation of heat anywhere. So whatever heat is coming inside the wall by convection will be equal to the heat traveling across the wall by conduction is equal to the heat leaving out of the wall by convection. These two have to be equal. Let me stop because people are becoming, as I can see, some people are leaving.
Sir,
Please tell me.
okay, can you repeat why is it a T infinity?
Infinity means the temperature is not infinity. That infinity means the temperature at a sufficient away, at a distance sufficiently away from the wall, where there is no change of temperature. At a distance, even if you move infinitely away, or even if you move just beyond the thermal boundary layer, the temperature does not change. Okay. That is called the free steam temperature. And normally free steam temperatures are indicated by T infinity kind of. That is symbolic representation of free stream temperature, where the temperature is not changing, where it does not sense the presence of the wall. You see this thing. If you are inside the room far away from the wall, whatever the temperature you sense, you come near the wall, you can sense a local drop in temperature. If you go, suppose you are in the cold condition, if you move towards the wall, if you sleep very near to the wall, you'll catch cold because you are sleeping very near to the wall means where the temperature is quite low. So maybe your head may lose heat from continuously from the head to the wall. So it should not be very close to the wall. That is a region called as a thermal boundary layer. If you go inside that thing, then you can sense a drop in temperature. If you are inside the thermal boundary layer, there are two thermal boundary layers here and this side. Wherever there is a fluid, there is a heat flow, there is a temperature change has to be there. So the region where there is a change, that is called the thermal boundary layer, and the region beyond that is the free steam zone. In the free steam zone, we indicate the symbolically we write it as T infinity. Now there are two T infinities, one on side 1, another is on side 2. That is called free stream. Not necessarily you have to go really infinity away. If you move by 1 feet, you can see the temperature remains unchanged. But if you come close to maybe say 5 inch, 6 inch near to the wall, you can sense a drop in temperature.
Okay, sir.
Sir, in the previous class, you had mentioned that calculation of H for convection becomes a hectic job. So, sir,
Yes.
why are we using H here?
If you know, then you use it. Okay. Then your job will be to create the value of H. You are not here to calculate this thing. Your intention will be to create, to know the value of H for situations which are for which the values of H are not known. The moment somebody finds it out, it becomes available to the entire scientific and engineering community. So it is available for cases, and for those cases you can use those values of A, and for cases which for which H values are not known, there only the requirement for an engineer or a educated person is required. And that is why he will be recruited for an organization so that he can give that knowledge to the organization, how to find out H. Okay. What I
Okay,
am
sir.
talking, there are two levels of people who will be involved. One people will be the user group of people who will be interested to know the value of H so that they can easily use it. And there will be another group of people who will be creating this type of knowledge. So one group of people will be knowledge creator, one group of people will be the knowledge user. Okay. So what we are expected to be is the knowledge creator, where we'll be able to know the value of H for situations which are so far what you call uncharted, unused. And if you have a used situation at the same time, you should not try to find out something that is already reinvent. You should not reinvent something that is already there. You should be also knowledgeable enough to know that for this situation, the value of H is known. So let me use that thing rather than trying to rewrite that thing. Okay. So you will have two jobs: to know what is known and to create what is not known. Okay.
Okay, sir.
Today is 14. Let me give you attendance and then do. Last week, did I take this class from last previous week? Did we take the class from 11? I had a sense, so I was sleeping actually comfortably. I had an idea that the class is from 11. That maybe because maybe in the first week I have taken the class at 11. Is it like that or what? So the class is on Monday, it is at 1 to 2. Then Tuesday and Friday, it is from 10 to 11. Is it? Okay, 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 I remember. Now, actually, and then just I was half sleep, asleep kind. Abhishek,
Present, sir.
Present, sir.
Shovik,
Present, sir.
56,
Present, sir.
Gustav, 59, 59, absent.